Welcome to today's explainer. If you follow the quantum computing space, you already know there's one massive, stubborn roadblock standing between us and a fully realized quantum future, and that is error correction. Quantum states are just incredibly fragile. But today, we're diving into a surprising new Nature paper from D-Wave, a legacy player in the quantum world that might completely rethink how we clear that hurdle. Get ready, because this is an absolutely fascinating approach to the problem.
To map out our journey today, we're going to cover 6 key areas. First, D-Wave's surprising quantum pivot. Second, we'll meet the dual-rail qubit. Third, we'll look at the error correction advantage. Fourth, the fast entanglement breakthrough. Fifth, the remaining hurdles they still have to clear. And finally, number 6, the road to 2028.
Okay, let's dive right into part 1, D-Wave's surprising quantum pivot.
To really grasp why this new paper is such a big deal, we have to look at D-Wave's history in the industry. Honestly, they've always been a bit of a legacy oddity. While tech giants like IBM and Google were going one way, D-Wave built quantum annealers. These are highly specialized machines designed to solve a very specific class of optimization problems. They're incredibly powerful for what they do, but they aren't general-purpose computers. Recently, though, D-Wave made a massive pivot. They decided to enter the mainstream race, focusing on general-purpose, gate-based hardware using fluxonium qubits. And to jumpstart this totally new effort, they actually acquired a Yale University spin-out called Quantum Circuits, placing a huge bet on a very specific, unconventional type of architecture.
So what exactly is this architecture? Let's move to section 2, meet the dual-rail qubit. How does this new hardware actually work? Well, imagine a microscopic track with 2 linked resonators, kind of like a left side and a right side. A single photon is placed into this system, and it exists in a superposition of both left and right simultaneously. That photon is your qubit. Now, here is where it gets absolutely brilliant. Sometimes a photon just escapes the hardware, right? In a normal quantum system, losing your data is a silent disaster. It's literally like dropping your house keys on a walk, but not realizing it until you reach your front door. But in this dual-rail setup, which is also known as an erasure qubit, when that photon escapes, the information is cleanly erased, triggering a built-in alarm. We know instantly that an error occurred. And in the quantum world, an error you can clearly see is actually a good error.
Now, why does this matter so much? Let's get into section 3. The error correction advantage.
This built-in alarm system is the ultimate weapon against hardware bloat. If we break down the hierarchy of errors in a dual-rail system, it's incredibly skewed. Photon loss, that highly detectable erasure we just talked about, is by far the most common error, happening at a rate of about 0.5%. Phase flips are a very distant second, and bit flips, they're practically non-existent, occurring way down at the 10 to the minus 6th level. This isn't just some random assortment of bugs. It is a highly predictable hierarchy.
Because these errors are so incredibly predictable and utterly dominated by that detectable photon loss, D-Wave can completely rewrite their engineering strategy. They don't have to build massive, bloated architectures with thousands of extra qubits just to run really complex catch-all error correction codes. Instead, they can use a much simpler, more compact code explicitly tailored to look for missing photons. This means they can devote far fewer physical hardware qubits to create a single, stable, logical qubit. D-Wave is betting that this specific efficiency will be their shortcut to useful quantum computation. And why does this matter to us? Because sidestepping that hardware blow could literally be the difference between waiting decades for a practical quantum computer and seeing one in the next few years.
All right, moving on to section 4, the fast entanglement breakthrough. Having a highly detectable qubit sitting completely still in isolation is great, but to do actual math, you have to make them interact. So D-Wave placed a tunable coupler between 2 dual-rail qubits to test if they could successfully entangle them. The process they published in Nature is stunningly simple. Step 1, you activate the connection so a control qubit partially occupies the coupler. Step 2, you wait just 200 nanoseconds. Step 3, you shut the connection off. That's literally it.
The total time for that entire entanglement process, from start to finish, is just 500 nanoseconds. D-Wave successfully proved that not only do they maintain the high fidelity of these dual-rail devices, but they can execute these crucial entangling operations at blistering speeds.
But honestly, speed was only half the battle here. Trevor Lanting from D-Wave explains the true victory of this experiment perfectly. He says, "One of the fundamental things that we're very excited about with this 2-qubit gate is that it preserves the error hierarchy. This is a massive deal. Normally, when you force qubits to entangle, you distort the system and introduce a chaotic mess of brand new, unpredictable errors. But here, photon loss remained the dominant, easy-to-detect error. They successfully entangled the qubits without ruining the exact feature that makes them so special in the first place.
Let's bring this back to reality for a second. In Section 5, remaining hurdles to clear.
As exciting as this Nature paper is, we definitely need a reality check. There are still major scientific roadblocks standing between this lab experiment and a fully commercial machine. First, they observed a quadratic decrease in fidelity as gate operations increase. Basically, as they string more and more operations together, the error rates rise way faster than expected. They suspect this is due to a drift in their calibration parameters, meaning the delicate tuning of the hardware is wavering over time. On top of that, they urgently need to perfect mid-circuit erasure detection. Right now, they're really good at detecting lost photons at the end of a process. But true functional error correction requires spotting those losses actively right in the middle of a running calculation.
Add to that the fact that interpreting all this error data, which is called the syndrome, requires immense classical computing power. However, Trevor Lonting is actually highly optimistic about this hurdle too. He notes that the dual-rail system provides a much richer set of information in the data stream that's flowing off the processor. Because they know exactly what kind of errors they're looking for, this highly detailed data stream should ultimately help reduce that classical computing burden as they scale the technology up.
So, what's next? Let's jump to our final section, the road to 2028.
Let's look forward at D-Wave's timeline for turning this experimental success into a scaled reality. 181. That is the magic target number of dual-rail qubits D-Wave plans to successfully link together by the year 2028. Reaching this 181-qubit milestone is absolutely critical, because it will give them exactly enough horsepower to rigorously test surface code error detection schemes at scale. If that hardware performs as expected, the next colossal challenge will be linking enough of them to host hundreds of fully error-corrected, logical qubits. So I want to leave you with this final thought to ponder. Will D-Wave's unconventional bet on dual-rail qubits be the key that finally unlocks practical, error-free quantum computing? They started as the odd one out, building niche annealers, but by pivoting to this highly detectable erasure qubit model, they just might be rewriting the rules of the entire quantum race. They're proving that sometimes the best way to handle errors isn't to fight them blindly, but to build a system where you can clearly see them coming. Thank you for joining me for this explainer, and definitely keep your eyes on 2028.